now, today, we're gonna be talking about a very important aspect or subject in control systems, that is identification. So in most of the class, we talk about having a linear system, and then we have a PID controller or a PI controller, how we connect that. But there is one question or one aspect missing in this whole discussion is, how do I get a transfer function that model my system? Right? Once I have that transfer function, I can understand what are the poles, I can understand the gain, and I can design my control system. But most textbooks, they already give us a transfer function. But how do I get from a real physical system, how do I get a transfer function? This process is called identification. Like, it's just a beautiful name to say that I'm gonna take a physical system and I'm gonna find out the gain, the poles and zeros of that system. Nothing else, like nothing more. So let's take a simple example today. In another opportunity, we can go to a more higher order of identification, but today let's stick to the basics, to the concept. So let's pick a motion control system, and we are going to be identifying a first order model for that system. If you have read the textbooks on motion control, you're going to see that a motor can be modeled as a first order or a second order, even some motors, high-speed motors, higher order than 2. So here we're going to stick to first order. It's an introduction to identification. So this is the idea here. Let's put first a control system, a full control system. So I have here a PI controller that is, I have a PI controller that is going to be driving some sort of D2A that's going to be driving some sort of power driver.
Julio, look, I have a fourth-order system here.
Yeah, he has a control system in his back. So this is controlling a motor, and the speed of that motor we already discussed about the ground. So this is a power ground. This circuit here is going to be a power ground. I'm going to put PG. But this one here, which is going to be connected to another ground. And the other one, the PI controller, is going to be connected, because it's a digital controller, is going to be connected to a digital ground. So we have this system, and then we are measuring the speed here. So this is simply a speed controller, for example. So what I do, I come here, plus, minus. That is my speed reference. I'm not going to go into details how to set the speed reference on this. This is part of a control system course. That's not the objective here. The objective is to understand how the identification sits here. So we have this, and we measure the speed just for completeness. Normally we put a low pass filter because the speed will have noise. So normally we put a low pass filter just to remove the noise. This is not a critical filter, and we go here and we close the loop. That is a speed control. So this is the speed here, goes filtered, sent there. The PI controller is going to receive it. Is going to calculate a control signal. This control signal is translated from digital to analog somehow. Very often we use a PWM modulation technique to do that, but there are other ways. That's not the only way. So the point here, we need a D2A somehow, and this PWM signal goes into the a DC-DC converter. A DC-DC converter. Why? Because this guy here is a DC motor. If this was an induction motor, I would need a different kind of controller here. So this is a DC motor. I can use a DC-DC converter. So the output, I adjust the output, the voltage at the output, to adjust the speed. So this is the control system. But the problem is, in a control system class, is how I design the PI controller. One important information is if we look here, I need to know the gain and the poles and zeros for a system like this. That is the first step to be able to design. My objective is to design API controller, but the first step, I need to understand what kind of system I'm going to control. I'm not gonna go into the mathematics for the system, but this system here, I'm gonna put it in red. It is normally modeled by something like this. That is one possible model. We may have other ways to model it. A first order model would be something like this. Over S tau Mac plus 1. First order, S to the power of 1. So what I need to characterize this whole system is a gain and a time constant. If, and that is the case here, if I'm driving this motor by voltage, so I have voltage and my output is speed. So this is voltage and the output is speed. If I have this system controlled by voltage with the output being speed, this time constant here is called the mechanical time constant. Note that there is a definition. A motor does not have a mechanical time constant. That is only if I'm driving the motor with voltage and the output is speed. In other words, what I'm saying is, if the output T or S equals K S tau Mac plus 1, and the input is voltage. If the input, I'm repeating myself many times to make this really clear, that is normally a confusion. When the students look, they think that the tau Mac is the time constant of the motor for any case. That's not true. There are other ways of using a motor that tau Mac has no meaning there. If I'm driving the motor with voltage and the output is speed, then I have tau Mac, only in that case, which is called the mechanical time constant. So our objective here today is to do the identification of the first order model of this motor. So this means that we wanted to identify the value of tau Mac, and we want to identify the value of the gain. So let's look at the first experiment to do that. And I'm gonna try to not erase it and separate in two parts. First one, K. And we're gonna do it graphically, and then explain how we can do that experimentally. Suppose that I go and I apply a voltage. So, for example, voltage is 0, and if that motor is, for example, a 12 volts motor, I apply 12 volts here. So this is the input. What's gonna happen to the motor? The motor is gonna do something like this. The speed. At this point, it's gonna do something, and at some point, it's gonna stabilize. So it means that for this speed, for this speed, I have a certain voltage there. So it's easy to calculate the gain. Gain is equals to omega divided by the input voltage. That's a simple experiment. Just drive the motor with a certain voltage and measure the speed.
Yeah,
If the motor is 12 volts, it's not a good practice to drive it with 12 volts, because 12 volts is the maximum. At the maximum, there are always no linearity. Like the relationship between these two parameters may not be linear. So it's more reasonable that instead of 12 volts, we drive it with, let's say, 6 volts. which rough in the middle. And then we take the gain at the middle. That makes more sense. So, but in any case, the gain is simply the final speed divided by the input voltage. So we already identified this part here. So now, how do we identify the second part, which is tau mac, the mechanical time constant? The mechanical time constant, we do a similar experiment. We apply 0 volts here, 6 volts. This is the input voltage. The motor is going to do something like this. The speed is going to grow until it stabilizes. If we take this 63%. So this point here, this value here is 63%. If we choose this value here to be 63% of the final speed, I'm going to call the final speed WF. If we choose this point here to be 63% of WF, then this time here is tau mac. So the only thing we need to do is to apply a voltage change, record the output in a graphics, look at the 63% of the maximum value, and we know that the time from here to here is the tau mac that we're looking for. This process is called identification. Why? I'm taking a physical system and applying physical voltage, measuring physical speeds, and calculating a model that approximates the behavior of the motor. Now, with this information, we have tau mac, we have K. We can use that information to choose what kind of PI controller design technique we're going to use.
But you choose if it's a first order or second order, you choose?
Yes.
And if it's a second order?
It is your choice. Like, it's a very good question. So we understood how the identification is done. We are not going to discuss today how to do identification for a second order, but let me show you what we are missing if you choose the wrong thing. I'm going to erase this. And I'm going to use two different colors. I'm going to use for a first order, more general. This is for a first order. The response is going to be like that.
Again, that's voltage versus speed.
That is, no, this is time, and this is speed. So this is the omega f, final speed, and the time constant was here, the 63% as we did before. Let's see what is the difference to a second order.
Okay, so you look at this.
If we have a second order system, probably it depends on the poles of the second order, so it can change a little bit. But for a second order system, the response would be more like this.
Oh, okay.
A second order system has more degrees of freedom. So depending on the position of in the Laplace plane, depending on the position of the poles, we may have the system to behave like this. We may have the system to behave like this. Or we can have the system to behave like that.
Damp or under?
Depending on the damping factor, which is a function of the relationship between the poles. To write here, so the transfer function for a second order is going to be something like this: K, S plus tau 1, S plus tau 2. That's for a second order transfer function. Compare that with the previous one. For a first order transfer function, it's K over tau 1 as tau 1 plus 1. Or we can rewrite in a different way. Such algebraic manipulation we can put in a format like this. If you prefer just to be similar to that one, we can rewrite the two that we saw before and this one that I'm going to write now. They are 100% equivalent. We can write like this. I'm going to put tau 0 here. I don't want to, because this one may not be the tau 1 that we have here. So this is a first order, which is going to give a response like this. The second order, depending on the tau 1 and tau 2, where they are in the complex plane, we may have these different types of response. So to do the identification of a second order system, we do the gain the same way we did before, because this gain is the same. But to find out tau 1 and tau 2, we need a different process. We're not going to discuss that here today. We're going to discuss that in another time. Did I answer your question? So we have saw that today what the identification is. Identification is taking a physical system and deriving a model to it. The model can be first order, second order, or even higher order. There are different ways to do identification. We presented here one that is convenient for a first order system. In the experiment that you're going to be doing, you're going to be taking a motor, you're going to be writing a code into the Arduino controller that will be driving a DC-DC converter to create a voltage change at the terminals of the motor. That voltage change is going to cause the speed of the motor. This is going to cause the motor to accelerate. So the motor is going to accelerate and will create a response like this and stabilize. So you're going to use the visualization tool to record measure the speed and store it to be used later in a spreadsheet, in Excel or something else. In the second part of the experiment, you're going to reduce the voltage for the motor to go down. The same thing is going to happen. It's gonna, if I reduce the voltage, the speed is going to go down and it's going to stabilize it somewhere. In the experiment, we don't start from ground. We always try to work far from the two limits. The two limits are 0 and 100%. So the experiment goes from here. If the maximum speed is here, we don't go up to the maximum speed. And when we bring it back, we don't bring it back to 0 either. The objective is to avoid the non-linearities that every physical system has. So we stay something in the middle. If we're going to have, like, if this speed here, maximum speed, is going to be 80% of the maximum speed, or 70% of the maximum speed, doesn't change the experiment. Same thing on the other side. If this is 10% of the maximum speed, or 20% of the maximum speed, it doesn't change the experiment. The message is stay away from 0 and stay away from 100% to avoid the non-linearities. So after you finish and you drive the motor, you can successfully drive the motor to accelerate and decelerate. Then you should start the visualization tool and capture this on the screen. The tool has some features that you can record that in a graphics form, or you can export it to be used in a spreadsheet like Excel. So it's your choice which process you want to use. This is a very good way to you to capture that data and use to prepare your lab report later on. You're gonna get some very beautiful graphics that you can play with. And that concludes the presentation today.